Alright, so we're going to start talking about buffers. And so buffers are a little bit hard to understand until you get the hang of them, but they're actually really easy. What happens is a buffer has both acid and base in the solution at the same time, and so it can neutralize either acid or base that's added to it. Now you ask, well, how do we put both acid and base in at the same time and not have them react with each other? Well, it's because we use the conjugates. So a buffer has either lots of weak acid and its conjugate base together, or lots of weak base and its conjugate acid together. So if that sounds a little bit confusing, just hang with me and we'll keep talking about this. So if you have something that has carbonic acid, for instance, and its conjugate base, so its conjugate base would be HCO3 minus, when additional base is added, then it's going to react with the acid and be neutralized. But if you add acid to it, then the weak base, the conjugate base, will react with that. And it just keeps it in a nice pH range. It keeps it from changing pH at all in either direction. So a weak acid or base by themselves don't contain enough conjugate to be a buffer. So when you put like acetic acid in something, it doesn't have enough conjugate because remember, it doesn't ionize completely. It doesn't ionize very much at all. That's why it's weak. So the conjugate base, there's not going to be a lot of it. So what we do is we actually add the acid, and then we add the conjugate base itself by putting it with like a sodium salt, for example. So you have to have significant amounts of both a weak acid and its conjugate base, or vice versa. So, for instance, in this case, we could put acetic acid, and we could also put a bunch of sodium acetate in there. If we put them both in the same solution, then the acid would neutralize any base that's added, the base would neutralize any acid that's added, and it keeps the pH constant. So what you're looking for, you can't do this with strong acids or strong bases, obviously, because their conjugates are not acids or bases. You can only do it with weaks, and you have to have both the acid and the conjugate base, or the base and its conjugate acid. So looking at these, which one's a buffer? Well, this one has a strong acid, so that's out. This one has a strong acid, so it's out. This one has a solution that's neutral, so it's out. The only other option is D. It's got a weak acid, and it's got the conjugate base attached to a sodium salt. Now, obviously, it can be any neutral salt, any neutral metal, but that would make a buffer. So how do you calculate the pH? Well, to do this, we make an ice table, and we're just going to have more starting points. It's sort of like doing the mixture of a strong acid and a weak acid. You're going to have a starting amount here and a starting amount here. Should actually be a minus because you're putting in both the salt and the acid. This is called the common ion effect because you're starting with an ion that is already going to be produced by the ionization of the acid. So it's just an ice table like normal. Let me show you how to do this. Calculate the pH of a buffer solution. It's 0.1 molar in acetic acid, 0.1 molar in sodium acetate. So what we would do, we've got to get our equation, HC2H3O2. Then we're going to get our salt in here. Alright, so balanced equation, okay, we're good. Let's do everything that we need to do. Ice table, HC2H3O2, H3O, actually, I kind of don't want to do the lines, I don't have very much space. H3O plus, C2H3O2, ice. So, I'll put my 0.1 molar up here and 0.1 molar here. Then, we're doing the forward direction, minus x plus x plus x, 0.1 minus x, x, 0.1 plus x. And then, oh, I gotta find my k-value page. Sorry, I should have had that prepared. Here we go. Acetic acid is 1.8 times 10 to the negative fifth. So 1.8 times 10 to the negative fifth equals, well, we can use the x is small because of how small the k value is. So what we actually end up with is 0.1 x on top and 0.1 on the bottom, because it would have been 0.1 plus x times x over 0.1 minus x, and then these both go to 0. Well, those cancel, and we end up with an x being 1.8 times 10 to the negative fifth. If I take the negative log of that, negative log of 1.8, we get 4.74. It's awesome. Okay, so that's all you got to do to solve for the pH of a buffer. Since we just did that one with different concentrations, I'm going to go ahead and leave you to do that one on your own. The answer is correct there. Also, the answer is there, so you can work them out, and if you have troubles, then email me. I can try to help you. Another way to find the pH for a buffer solution is using the equation called Henderson-Hasselbalch equation. You can do this by plugging in the concentration of the base and the acid and the pKa of the acid. So this only works when you can use the excess small approximation, but like I've showed you, most times with acids and bases we can't use it, so it's a good bet that you can use Henderson-Hasselbalch, especially on the AP test, because they don't want you to take too much time. So what you would do is, well, actually, let's just go ahead and move to the practice. So the equation, you'll want to memorize it, is base over acid. So if that was confusing you, it's base on top of acid in the whole log thing. So calculate the pH of a buffer. Well, pH is equal to pKa plus the log of the base over the acid. Well, in this case, the base is sodium benzoate because it's the salt, 0.150, over the concentration of the acid, 0.050, okay? The pKa is going to be the negative log of 6.5 times 10 to the negative fifth. So plug all that in. Negative log of 6.5 times 10 to the negative fifth equals 4.18, so pH equals 4.187 plus the log of 0.15, so log of 0.15 divided by 0.05 is plus 0.477, and if you add those up, pH is equal to 4.66. So that's all you got to do there. This is what your homework's going to be about. So I hope that's helpful. Let me know if you have questions.